Hello. This is um, this is going to be my introduction to my progression towards writing a compiler from scratch in assembly. And you might ask yourself, why would you ever want to do that such a thing? And the answer is actually quite simple because I already wrote a compiler from scratch in Java for my bachelor. It didn't go that well. It went okay. It was kind of slow, and I guess it was maybe because of the techniques I used. I wrote it in Java, so it was heavily reliant on object-oriented programming, and I did use some visitor patterns, and it was actually kinda advanced in some sort. It was actually very advanced. I used some of the more modern features in Java to basically to develop the compiler, and in the end it was just too slow, and I benchmarked it, and I discovered that the actual primary problem with the compiler was the parser generation stuff, and for the actual project for the bachelor I wrote the parser I used was actually one of my own creation. I wrote a parser generator for the bachelor. So I wrote an LR1 parser generator. So you will provide the program with a context-free grammar, and it would provide you with a parser table that was able to parse the language that you wrote. It was actually kind of advanced, and when I think back on it, it was more than what we were supposed to do, and I guess that's maybe where I went wrong. I guess I used too much time on the programming part, and not too much time on the actual report, and I can see why that might be a problem, but I'm not really a person that really likes to do reports. Like, I have no problem writing them, but I would much rather just write actual programs that do stuff. I feel that reports are maybe a waste of time, at least on my level. Like, writing a bachelor is basically a waste of time because everybody knows what you're talking about. You're not really figuring anything new. Like, you're not really finding anything new. You're just like repeating stuff that other people have already made. Like, I made a parser generator. You can just use Python. I made a regex compiler. You can just use Flex. I did that from scratch, and whatever. Anyways, but what did I learned a lot of stuff from actually writing the compiler from scratch in Java. I learned that sometimes I have always had the belief that compilation speed and runtime speed actually didn't matter, because I have never actually run a big program before. But now that I actually have, I can see that if a compiler runs for like 2 seconds, that's unacceptable basically. So and my compiler ran for like, just to load the parser table, it took like 2.5 seconds, because the parser table for my language was something like 50 megabytes or something. It was stupid, so fucking stupid. It was an LR1 parse table. It was not an LA1 parse table. It was the first one, I could easily convert it to an LRLA parser, but I didn't want to spend time on it. I had already spent a lot of time like developing this parser generator. Anyways, I wrote a parser generator called Parsley, where you can provide it with some CFG language, and it would spit out a parse table in LR1 format that you can actually parse, and by using this parse table I was actually able to make my front end. So in a compiler you have different steps to it. So you have the front end, and then you have the back end, and depending on how you actually make your compiler, it's different. Like one step might actually be more difficult than the other. If you use LLVM, the backend is kind of easy. If you do it yourself, it's actually kind of difficult because you have to know the assembly. You have to know all the backend stuff. Yeah, whatever. So my program called Parsley is able. I don't know it. Do you guys know Haskell syntax? I kind of like Haskell. Parsley is able to take some CFG as an input, and it's able to provide how would you write this? So it takes in a CFG, so a context-free grammar, and it outputs a parse table of some sort. And this parse table you are able to use during runtime to actually run or parse your language. Basically, this means that the function parsley takes in as a parameter a context-free grammar, and it produces a parse table based on the context-free grammar. So this is the input and this is the output. Yeah, so I won't go into the depth of it, but it was actually kind of complicated. I'm proud of it, but it was too complicated for what it was actually supposed to be used for. So yeah, whatever. So I decided to go back to the roots, and that's why you can see my folder currently is called C++ compiler generation assembly 0. And that's because the goal for this project, at least, is to write a compiler from scratch in assembly instead of just Java. And I have already written a compiler from scratch in Java, and it was super slow, but that's primarily because of the way I did it. I used a parse table instead of just writing a recursive descent parser, which is objectively faster. Yeah, it's just faster. When I ran the compiler from my laptop, it took like maybe 10 seconds to construct the parse table, and also to compile maybe 10 lines of codes. And it didn't really matter if you compiled 10 lines of code or 100 lines of code, it would always take 10 seconds. And it just shows you the overhead of just using a okay, I was granted I was creating the parse table, and then I was running the parse table, and I actually did serialize the parse table later, and it reduced the time by like 80%. So it went from like 10 seconds to 3 seconds. But most of the time was spent loading in the file, because I saved it to a file and then I load the parse table. It's still like it's stupid. So I think I might just have done it a dumb way. Anyways, so for for this project, I actually aim to create a compiler from scratch written in assembly. So the goal is to take in something written in input.a. Let's see here. So kind of like this. So it kind of looks like Python syntax. So define a. This is a function called a, and we want to print 2 plus 2. Currently it's just semicolon because of some of the earlier stuff. Yeah, that is something you're going to recognize when you develop your projects. You have to see what can you do. Okay, I can see, okay, this define is a define token, but I actually had a problem where you never stopped, so I have to add a semicolon to actually make the parsers, the tokenizer stop. It has to be able to recognize an enough parse token, so that's why I added this symbol. Yeah. And it wasn't actually that difficult. I just had to. The primary difficult part was actually to remember how assembly was written. This actually seems like quite a lot of code, but it's just if this then that, if this then that. It's just a bunch of if statements. If rax is equals to 1 and rax is a register, so just think of it as a variable. If variable rax is 1, then do this. If it's 2, then do this. If it's 3, then do this, basically all the way down. Yeah. So anyways, what I have so far is I have written my Alexa in assembly, and it's capable. Currently we can fetch a token, and it produces, it outputs a, have I written it? No, I haven't, not yet. Anyways, currently it's capable of recognizing left parentheses, right parentheses, curly brackets, and the bracket syntax, like this syntax. And I'm going to use this for this list syntax or array syntax in my source language. And currently is capable of recognizing numbers. So anyways, it might seem kind of obscure. If you've never seen assembly before, I can maybe explain it. Okay, so don't look at this here. Let's just imagine that the input is something like this. 152. Okay, so this is the input, right? I think I can do this. Yeah, nice. So, oh, nice. Okay, so imagine this is the input, 152, and we want to somehow tokenize this so we can convert this, so we can recognize this and distinguish it from like a word like this, or maybe a variable called variable awesome or something, right? And maybe you want a function called a, and it needs to do some printing where it adds 3 and 5, 65 together or whatever, and that's what we want to do. But let's just imagine we want our Alexa to recognize the number 152. So this is actually why I kind of like assembly, because you have to be very, you have to think like the computer does. Like, what is this? What is the input right now? The input is the character 1 and the character 5 and the character 2. And some of you might actually not know it, but the character 1, we can see here, the input 152, 152, like us humans are able to deduce this as being the number 152, but from the computer perspective, it's actually, if we look at this column, I have to scroll up more. This is a decimal. Decimal means 10. So it's base 10. So this is what normal humans reads. And then we also have hex, and it means base 16, and oct, which is base 8. So if you look at this column and you go down to 0, you actually see 48. So what the computer reads when it sees this 1, it's actually not a 1, it's actually 49, because that's how the Americans did it. They wanted to have the number 0 as the 48th character in the keyboard, and the number 1 as the 49th. That's just how it is. So whenever you read a character, and a character is basically 8 bytes, and what is a byte? A byte is 1 byte is 8 bits. And how much can you represent by 8 bits? You can represent 128 different characters. So we have from 0 to, you can see here, decimal, 0 to, if you look down here, 127, which is 127, and the 0th, so it's 128. So that's how many different kind of characters you can represent with 8 bits. Oh, my neighbors are going to bed now. It's also very late. It's actually very late, but that's okay. So from the computer's perspective, we are actually reading the numbers 49. 49 followed by a 5, which is 53. Followed by the 2, which is 4. So we somehow have to convert the sequence of 49, 53, and 4 to the number 152. And one way I thought of doing that is actually doing, okay, first we have to count how many numbers are in this, let's say, word or sequence. Let's imagine there was an A here. You would only actually, like, if you were a human and you were to read this, you would read 152, and then you would read an A. So you would read this as, okay, 152, and then you would just stop. Okay. And when we're dealing with assembly, that's also how you have to think about it. So I made my program stop after it read all the numbers. We can see this here. It moves 1 byte, and 1 byte is what is necessary to display 1 character. And RDI is our input buffer. We can see this as in. So RDI is basically the address of this in variable, which currently stores the value 152A. And then we can see here RCX is actually the index into this buffer. So we could imagine at the start it would be index 0, so it would actually see this first character here, the first one, which is as 1, and then it moves 1 byte, which we can see here, move 1 byte from this address to this address. And this is something you have to know. You can look it up just like I did. AL is a part of the register called RAX, which is a register, the primary register. This is the lower 8 bits of the register. Then we move 1 byte into this register here. So one register, RAX for example, in modern systems is actually 64 bits. So we have 4 of these, where we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So RAX is this entire span. So this is like the entire RAX register. So the lower AL would be this part of the register. Anyway, so we move the first byte, which is the 1, into AL, and then we just see, okay, is this within our number range? And I have done some clever, it's not really clever, but it's it works, whatever. We can see it here in the config. If we scroll down, we can see number 0 is actually just the letter 0, ASCII character. And if we go back and look, the ASCII character is 48. So in actuality, this is actually the value of 48. And this has the value of 57. So it's just a way for me not to have to remember what the actual value of it is. Yeah, so I can, these parentheses is actually, okay, what is written in this address, which is this. So this is like a variable, and it has an address, and what is written in that address is the value character 0, which is the value of 48. So you can see, okay, what is the address of number 0? We look in here, we see number 0. Okay, this is the address. And okay, how do you figure out what the address is? You as a human, you don't figure it out, but the linker does it. You say LD. The LD is actually a part of the linker. It links your .o files. Let's see if I have any. Make. It links these files .o. It links all of these files together into a executable file. So it links all of your markers, like these are going to be converted into some sort of number like this. It's going to be an offset. Yeah, so it looks at this number and then it says, okay, what is the actual value of this? Is this going to be, it's just a 0, so this is a zeros index. If it had 2 numbers, then it's just going to be 0, and then you can offset into it depending on the type. I actually don't know how you would explain that, but depending on your relative type, how much are you going to address into this? It depends on what your type currently is when you're addressing into it. Anyways, but currently we are addressing into it with 1 byte at a time. So we're going to load this address, okay, number 0, okay, we will ask the linker, okay, where's this number 0? It's this. And then the parentheses means, okay, please dereference this and then move it into AL. And dereference is basically the same as let's just say A, and then we can have a pointer, and then you can say printf the dereference P. So this is basically the same. So P is the same as doing star P, basically. This is going to be the same as this. It's basically just dereference. So we want the value of whatever is stored inside this address. So as you know, P is currently storing an address 2A somewhere in memory. And we want to now read the address, or we want to read the address P and go to that address, and we want to read the value stored at that address. That is what is going on here. Oh. Yeah, but that is basically what it does. So it says, okay, are we currently reading a 0? And then we say JL, is this less than this number? And if we look at the ASCII table, which is here, this part, we say, okay, are we currently looking at a number smaller than 48? Is the number AL that we are reading, is that smaller than 48? Then it cannot be a number, because then it's going to be one of these symbols. Okay, if it's smaller than this number 48, then it's going to be one of these symbols, right? Then it cannot be a number. If it is greater than 9, then it's going to be one of these symbols all the way down here, like all of these symbols. And jump less than jump greater, submit number. Oh yeah, I skipped this. Nice. Yeah. Right. So if we are smaller than this, then it's not a number. However, if we are greater than a 9, if we are in these characters, then we cannot possibly be a number. However, if we are not, then we know that we actually are part of a number. So we have to actually somehow register what the number is. I realize now that I'm actually kind of shit at explaining this, so I might actually not in the future explain it. I might just show how I derive it, how I do it. I don't know. Anyways, from here we see, okay, we actually have a number. Okay, we have a number. Okay, so now we need to store what the number is and from what index it currently is. So let's say we have the number 152 as in the config and the input file 152. Let's just remove this file. Delete. Okay. Now we have to store the index into our buffer. So imagine our buffer being something like blah 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 blah. Then we have to remember, okay, this index, this, right? This is our actual index into our buffer. So we need to store this, and we store this into the register R9, and from that point we can we will count, we will look until we don't reach a number anymore. So if from the moment we reach something like A or any other character, like a maybe an @ sign. Oh, why can't I make an @ sign? Maybe an @ sign. From that point we will only read these 3 characters. That is basically what this loop does. Oh, this loop reads all of the characters from here to here, which is this part. Yeah, basically again, read RDI, this is this buffer, RCX, that's the index, currently we are here, and then we move it into AL, which is this character right now. It's going to be a 1. Then we are going to compare the 1 here with the number 0. If we are less than the number 0, we are not, so we are fine. Then we're going to compare with the number 9. Is the 1 less than the number or greater than the number 9? No, it's not. Okay, then we're good. Then we can progress to the next number. So we have now successfully moved our pointer to this position. And I will do the same again. No, it's not this. It's not this. However, if we look at this symbol, the @ sign, it's actually, let's see, where is it? The @ sign. It's right here. It's actually greater than 9. 64 is the number of it, and the number 9 is 57. So it's greater than 9. So this fails. Okay. So now we know this is our start position and this is our end position. So now we need to convert these three characters into a number. And remember, this is not actually the number 152, it's the characters 1, the character 5, and the character 2, which are totally different from the number 152. Because they're characters and not a number. Because numbers in computers are stored as base as a 2's complement, depending on how many registers you're using for your number. But yeah, basically as 2's complement, usually with 32 bits, sometimes 64, depends. So that's how you actually register how many numbers are actually in it. And then you go, we want to actually convert these 3 characters, we want to convert them. So how we do this is first, okay, we look at the first symbol, it's a 1. Okay, and then we look, okay, it's 3 long. So now we have to multiply it with 100. Okay, because we need a 1 at the third place. And then we can add to it the next symbol, which is a 5. And then, okay, how far are we from the end? We are 1 from the end. So we need to multiply the 5 with a 10. So we can add 50 to it. And then the last symbol is a 2. So we can add 2. And then how far are we from the end? We are 1 from the end. So we can multiply 2 by 1. And then we get this equation, which is 100 plus 50 plus 2, which is 152. And this is our final result. So that's how we convert the characters 152 into the actual numbers 152, which is basically what this does. Here we see, okay, are we done? No, we are not. Okay, then we multiply with the art 11. We can see up here, that's just a 10, which is stored once, and then we decrease it by 1, which symbolizes us going from multiplying with 100 to multiplying with 10 with multiplying with 1, basically. So that's basically it. Yeah. Anyways, now I have shown you how maybe the conversion between different, let's say, representations are done. Let me just say, I'm kind of drunk right now. I'm actually really drunk, but who cares? You probably care because you're listening to this, but yeah. I've shown you how to convert one representation, which is ASCII representation, to number representation, which is basically ASCII to 2's complement, but you're not really using 2's complement because the hardware takes care of it for you. So anyways, I guess I'm getting off track right now. So far my progress is that I'm able to read numbers, I'm able to read brackets, I'm able to read the hårklammer, it's called in Danish. It's in English it's called a bracket, I guess. This is the parentheses, and these are tuborklammer. I don't know. They're called curly brackets, maybe in English. Yeah, I guess they are called that in English. Curly brackets. Yeah. Let's see how the actually program runs. Make clean. Make. It doesn't work. No. Config 14. Oh, because of this. Nice. Clean. Make. Oh, it works. Main. Okay, so we read a bunch of bullshit. Okay, let's try to just give it this. Make main. Okay. Okay, it doesn't work. Nice. What if we just give it ASD? Maybe def. Still. We're just printing a bunch of these. Okay. I think I might know why we're doing this. It's because we're not actually reading anything, because we're going into here. I say, have you really read a space? No, we haven't. There's no space in the input file. As we can see here, there's no space. It's not a bracket. Okay, let's just give it a bracket. What does it say with this? Save the file, make clean, make, run the file. Okay, it's still acts like crazy. Holy shit. Okay, let's look at main. Alright, we have a main, move it, push, get token, Do we have a JMP here? We have jumps. Loopers. We actually jump to the star. We do that sometimes. Yeah. Okay, can we say, let's just do this. Boom. Nice. Now we only read one token at a time. So now we have 2. Okay, we won't do it. Let's remove them. We read those 2. Nice. Good job. Okay. Let's figure out why we are complaining like we are. 11. Print. Right bracket, left bracket. SQC. Let's go down here. 2. Print BINT. Yes. EOP. 4. It might because we didn't write EOP. Boom. Nope, that didn't help at all. Okay, GDB time. Make clean. Make GDB main. Layout assembly. Layout registers. We want to break at the start. And we want to run it and step. Okay, so let's remember. We have the left parentheses, right parentheses. Good. So we should get the token. Move 0 into args. Yes. Read the first character, which is 40. Okay, we can open a new terminal. Main ASCII. Let's read 40. 40 is the left parentheses. Nice. Step. Okay. Yeah. Seems reasonable. It is a left parentheses. Move 5 to args. Yes. Return. RDI. Go to the next token. Yes. Push RDI because we don't want to lose it. Compare it. Printf. Nope, not that. Nope. This. Yes. Let's jump to this. Print it. And we print it. Yes. Syscall. Jump to the start again. Restore the pointer. Get the next token. Read 41. 41 is what? 41 is this. Is the other bracket. Nice. Just as we wanted. Nice. Let's go to the next one. No, not that one. It's this one. Boom. Yes, we want to print this. Syscall print. Nice. Go back to the start. Increase. Yes. Boom. Yes, 32. What is the next token? Let's see. It's a space. 32. Space. This one. Nice. That's correct. Let's see what happens. Yes. Remove white space. Okay. Yes, we read 69 now. 69 is up here, I guess. No, yeah, it is. E. Okay, what is E? It could be this EOP. Okay. O is going to be the next one, so let's see where we can find that. It's going to be 79. And 79. And then we were going to get the P, which is 80. We got it. Okay. Jump. Nope. Oh, interesting. Oh, that's the mistake. Yeah, I see now. Yes. Yeah. Yeah, now we are in a loop. Yeah. Alright. I see the mistake. Okay. So, yeah, nice. Okay, so the mistake is that it's almost 1:45. That's the primary mistake. Let's be honest, it is. But it is that I'm actually not parsing the other stuff because they are down here in the previous stuff. Okay. So it actually works like we wanted to. I just didn't remember because I went to a party. So that's nice. Yeah. I hope I will get better at doing this kind of stuff, but I probably won't. I think this is going to be the first part of my journey into writing a compiler. You're probably not interested. I guess it's probably going to be a minority of people who's going to be interested in this, but it's not really for you that I'm doing this. I'm doing this for myself. I wanna train my explanation skills, also my English. I wanna train my confidence in talking towards nobody. I wanna be comfortable in sounding like a stupid person. I'm very comfortable by doing that. I haven't mentioned it, but I was a teacher. I taught the programming course. I taught Java. Currently, I work at a company where I develop iOS apps. Yeah, and I also do some C++ programming. But my primary focus of interest is actually compilers. That's my end goal, at least. Yeah. But let's see where it goes from here. Maybe you have some tips. Maybe I will get better at maybe explaining my process in this. I haven't really explained anything. I have just kind of done whatever I felt like. This seems very improvised, and it is very improvised. Yeah. Whatever. I'm going to do another one tomorrow. I'm going to upload it to YouTube, and yeah, I hope I get better. Anyways, I might go dance now in the clubs. Maybe Proud Marys. You can meet me. I love going there. if there's anyone from Odense. That's probably not going to be anyone from Odense, but who knows? Maybe I'm lucky. We can meet, we can hang out, we can dance. Yeah. Adios, mi amigos.